stochastic process. In this we are going to discuss the Mod-04 Discrete-Time Markov chain, and this is a lecture 1. In this lecture I am going to discuss the introduction about the Discrete-Time Markov chain, then followed by the definition and the important one concept called the one-step transition probability matrix. So, this lecture I am going to cover the introduction, definition, transition probability matrix and few simple examples also. Consider a random experiment of tossing a coin infinitely many times. Each trial there are two possible outcomes, namely head or tail. Assume that the probability of head, that probability you assume that is P, and the probability of tail occurring in each trial, that you assume it as 1 minus P. You assume that the P lies between 0 to 1. Denote for the nth trial, because you are tossing a coin infinitely many times, for the nth trial you denote the random variable xn is the random variable whose values are 0 or 1 with the probability of xn takes the value 0, that is same as in the nth trial you are getting the tail, that probability is 1 minus P, and the probability of xn takes the value 1, that probability is make it as P for the head appears, and already you assume that the probability lies between 0 to 1. Thus, you have a sequence of random variable x1, x2 and so on, and this will form a stochastic process, and assume that all the xi's are mutually independent random variable. Independent random variables. So, this is a random experiment in which you are tossing a coin infinitely many times, and for any nth trial you define the random variable xn with the probability it takes a value 0 with the probability 1 minus P, and it takes a value 1 with the probability P, and that is equivalent of appearing a head with the probability P and occurring the tail with the probability 1 minus P. Now, I am going to define another random variable, that is a partial sum of first n random variables, n xi's. So, the Sn will be sum of first n random variables. Therefore, the sum Sn gives the number of heads appear in the first n trials. It can be observed that Sn plus 1 is same as Sn plus xn plus 1. Since Sn is the partial sum of first n trials outcome, so the Sn plus 1 is nothing but Sn plus xn plus 1. You can also observe that since Sn is the sum of first n random variables and Sn plus 1 is Sn plus xn plus 1, and also all the xi's are mutually independent random variables, Sn is independent with xn plus 1. That means, here the Sn plus 1th random variable is the combination of two independent random variables, whereas the Sn is the till nth trial how many heads you appeared, plus whether it is a head or a tail, accordingly this values is going to be 0 or 1. Therefore, if you see the sample path of Sn plus 1, it will be incremented by 1 if xn plus 1 takes a value 1, or it would have been the same value earlier if this xn plus 1 takes a value 0. And also you can observe that Sn plus 1 is depends on Sn and only on it. It is not depends on Sn minus 1 or Sn minus 2 and so on, because it is accumulated the number of trials values over the n. Therefore, Sn plus 1 is depends on Sn and only on it. The Sn for different values of n, this will form a stochastic process. This will form a stochastic process, and now we can come to the conclusion the probability of this is a stochastic process. The probability of Sn plus 1, suppose this values is k plus 1, given that Sn was k, that means the Sn plus 1 value would have been 1. Therefore, the appearance of the head appears in the n plus 1th trial, and that probability is going to be p. Similarly, you can make out, suppose Sn plus 1 value will be k such that Sn is also k, then that is possible with the n plus 1th trial you got the tail. Therefore, that probability is 1 minus p. This is satisfied for all n. So, you can make out this is satisfied for n is greater or equal to, even I can go for n is greater or equal to 1. Not only this, similarly I can come to the conclusion the probability of Sn plus 1 is equal to k, given that S1 was I1, S2 was I2 and so on, Sn was k, that is also can be proved. The probability of Sn plus 1 is equal to k, given that Sn is equal to k. That is same as what is the probability that the value was same k in the subsequent trials. That is possible of appearing a tail in the n plus 1th trial. Therefore, the appearance of the tail in the n plus 1th trial, the probability is 1 minus p, or I can use the notation q. That means, the probability of n plus 1th trial, that distribution, given that I know the value till the nth trial, that is same as the distribution of n plus 1th trial given with the only the nth distribution, not the earlier distributions. And this property is called a memoryless property. The stochastic process, the Sn satisfies the memoryless property, or the other word called Markov property. The distribution of n plus 1, given that the distribution of one first random variable, second random variable, the nth random variable, that is same as the conditional distribution of n plus 1th random variable, given that with the nth random variable only, and this property is called a memoryless or Markov property. The stochastic process, the Sn satisfying the Markov property or memoryless property is called a Markov process. The stochastic process satisfying the memoryless property or Markov property is called a Markov process. In this example, the stochastic process Sn is the discrete time discrete state stochastic process. Now, I can give based on the state space and the parameter space, I can classify the Markov process, or I can give the name of the Markov process in a easy way based on the state space as well as the parameter space. So, when the state space S, the S is the state space, this is nothing but the collection of all possible values of the stochastic process. If this is of the discrete type, discrete type, that means the collection of elements in the state space S is going to be a finite or countably infinite, then we say the state space is of the discrete type. So, whenever the stochastic process is satisfying the Markov property, then the stochastic process is called the Markov process, or you can say whenever the state space is a discrete, then we can say the corresponding stochastic process, we can call it as a Markov chain whenever the state space is a discrete. Now, based on the parameter space capital T, parameter space is nothing but the possible values of T, whether it is going to be a finite or countably infinite, then it is going to be a discrete parameter space or discrete time, or it is going to be uncountably many values, then it is going to be called it as a continuous type. So, whenever the T is going to be a discrete type, then the Markov chain is going to be called it as a discrete time Markov chain. Whenever the parameter space is going to be of the continuous type, that means the possible values of capital T is going to be uncountably many, then we say continuous time Markov chain. So, in this example, the Sn, the possible values of Sn is also going to be, the state space is going to be a discrete type and the parameter space is also going to be a discrete type. Therefore, the given example, the Sn is going to be the discrete time Markov chain. So, in this model we are going to study the discrete time Markov chain. The next model, model 4, model 5, we are going to discuss the continuous time Markov chain. So, in general, whenever the stochastic process satisfying the Markov property, it will be called the Markov process. So, based on the state space, the Markov process is called as a Markov chain, and based on the parameter space, it is called a discrete time Markov chain or continuous time Markov chain, accordingly discrete type or continuous type. Even though I have given one simple example and through that I explained the Markov property, therefore, we will end up discrete time Markov chain, I am going to give the formal definition of a discrete time Markov chain. Formal definition of discrete time Markov chain, in notation we call, in short we call it as a DTMC. Consider a discrete time, discrete state stochastic process. Consider a discrete time this is a discrete time, discrete state stochastic process. Assume that Xn takes a finite or countable number of possible values. Unless otherwise mentioned, this set of possible values will be denoted by the set of non-negative integers S is equal to 0, 1, 2 and so on. Unless otherwise mentioned, you can always assume that the state space S consists of the element 0, 1, 2 and so on. Even if it takes other values also, you can always make a one-to-one correspondence and make the state space is going to be S is equal to 0, 1, 2 and so on. Suppose the probability of the x n plus 1 will be taking the value j, given that it was taking the value x naught is equal to I naught, x 1 was I 1 and so on, and x n was I. That probability is same as the probability of x n plus 1 will be j, given that x n was I. for all states, I naught, whatever be the value of I naught, I 1, I and j, and also for all n greater than or equal to 0. If this property is satisfied by for all states I naught, I 1, I comma j, as well as for all n greater than or equal to 0, then this stochastic process, that is a discrete time discrete state stochastic process, is going to be known as a discrete time Markov chain. So, basically this is the Markov property, and the Markov property is satisfied by all the states as well as all the random variables. So, if this Markov property is satisfied by any stochastic process, then it is called a Markov process, and since it is the time space is discrete and the parameter space is discrete, therefore, it is called a discrete time Markov chain. Then we say this stochastic process x n takes value n starting with 0, 1, 2 and so on, is the discrete time Markov chain. We can just have a look of how the sample path look like for different value of n, and the y axis is x n. Suppose at n is equal to 0, it started with some value. At x is equal to n is equal to 1, it would have been the different value, and n is equal to 2, it would have been the different value. So, these values are the either it could be a finite value or countably infinite number of values. Therefore, the state space is going to be discrete and the parameter space is going to be discrete. So, like that it is taking a different value over the n. So, this is going to be the sample path or trace of the stochastic process x n. Suppose you assume that x n is the state of the system at nth step or nth time point, and this x n satisfies the previous this Markov property, then the stochastic process is going to be called it as a discrete time Markov chain. And our interest will be, suppose the stochastic process satisfies the Markov property, our interest will be to know the two things. One is, what is the distribution of x n for n is greater than or equal to 1. You know where the system starts. So, x naught you know, your interest will be what could be the distribution of x n, that is nothing but what is the probability that the x n will be in some state j, and also what could be the distribution of x n as n tends to infinity. As n tends to infinity, or our interest will be finding out the distribution of x n. So, at any finite n as well as n tends to infinity, that will be of our interest. To compute this, you need two things. One is you need what is the distribution of x naught, that is the initial distribution vector where the system starts at the 0th step. What is the distribution of x 0? And also second things of your interest will be what is the transition distribution or how the transition takes place. What is the distribution of a transition from any nth step to n plus 1th step for all n. So, if you know the two things, the initial distribution vector as well as the distribution of the transition from nth step to n plus 1th step, using these two quantity you can find out what is the distribution of xn for any n, as well as we can find out the distribution of xn as n tends to infinity. For that, I am going to define few conditional probability distribution as well as the marginal distribution for the random variable xn. Through that, we are going to find out the distribution of xn for any n as well as n tends to infinity. So, the first one I am going to define the probability mass function as the p suffix j of n, that is nothing but what is the probability that xn takes the value j. So, this is the probability mass function of the random variable xn. What is the probability that xn takes the value j? That I am going to denote it as the p suffix j of n, where here the j is belonging to the state space capital S. This is the probability mass function of the random variable xn. Similarly, I am going to define the conditional probability mass function as a p suffix j k of n, that is nothing but what is the probability that xn takes a value k given that I need two suffixes, two index for here with the two variables m comma n. What is the probability that xn will be the state k given that xm was j. Obviously, the m is lies between 0 to n, whatever m and every n, and the j comma k is belonging to capital S. So, this is a conditional probability distribution of the random variable xn with the xm, and at the mth step the system was in the state j, and the nth step the system is in the state k, and this is a conditional probability with the two arguments m comma n. So, this is a probability that the system makes a transition from the state j at step m to the state k at step n, and this is called a transition probability function of the discrete time Markov chain. When the DTMC is a time homogeneous, this is very important, when DTMC is a time homogeneous, that means it satisfies the time invariant property. That means the p j k of m comma n depends only on the time difference n minus m. Whenever the DTMC is a time homogeneous, that means in the time invariant. So, the actual time is not a matter, only the time difference is the importance. Therefore, this is going to depends only on the time difference n minus m. In this case, I do not want the two arguments m comma n, I can go for writing p j k of n, that is nothing but what is the probability that in the m plus nth step the system will be in the state k, given that in the mth step it is in the state, it was in the state j for all n, and here j comma k belonging to S. So, the m does not matter, only the interval or the interval length of step n is matter. So, that means the system was in the state j and it is a transition into the state k in n steps, because the DTMC is a time homogeneous. So, the xm to xm plus n, it is valid for all m. For all n, we are finding out for the n step transition. This is called a n step because the DTMZ is a time homogeneous, and this is called a n step transition probability function. This is a n step transition probability function. Using this, we can define the one step transition probability, that is denoted by p suffix jk of 1, or we can avoid the bracket 1 also. So, you can write it as the pj or pjk, that is nothing but what is the probability that the xn plus 1 is equal to k, given that xn is equal to j for all n greater than or equal to 1. Obviously, for j comma k belonging to S, if you find out the 0 step transition probability, that values is going to be 1 for j equal to k, otherwise it is going to be 0. This one step transition probability, I can make it in the matrix form, as the capital P is the matrix, and that consists of a Pij, where the Pij is nothing but one step transition probability elements of xn plus 1 is equal to j, given that xn is equal to I. Here I comma j belonging to the state space S. You should remember that the state space S is consists of finite elements or countably infinite number of elements. Accordingly, this matrix is going to be either when S is going to be a finite elements, then the P matrix is going to be a square matrix. Since the Pij is the one step transition probability of a system moving from the state I to j in one step, and since it is a time homogeneous, this is valid for all n. This is valid for all n greater than or equal to 1, and this satisfies the one step transition probability matrix, satisfies two properties. The each entity will be greater than or equal to 0 for all I comma j belonging to S, because these are all only the conditional probability of system moving from the state I to j in one step. Therefore, either it will be a 0 or greater than 0 for all possible values of I comma j. The second condition, if you make the summation over j for fixed I, then that is going to be 1, I belonging to S. That means the row sum is going to be 1, because it is a conditional probability of system moving from one state to all other states. If you add all the other possible probabilities, then that is going to be 1. And since this one step transition probability matrix satisfies these two properties, and this matrix is P is known as a stochastic matrix. Because of satisfying these two conditions, the matrix one step transition matrix is also called a stochastic matrix. Now, I am going to explain what is the pictorial way of viewing the one step transition probability matrix or the stochastic matrix, that is provided by state transition diagram, or the other word, it is called a directed graph. The DTMC can be viewed as a directed graph such that the state space S is the set of vertices or nodes, and the transition probabilities, that is a one step transition probabilities, or the weights of the directed arcs between these vertices or nodes. Since the weights are positive and the sum of the arc weights from each node is unity, this directed graph is also called a stochastic graph. It is useful to visualize the discrete-time Markov chain, and it is also useful to studying the properties of the discrete-time Markov chain. I am going to explain the discrete-time Markov chain with the three simple examples. The first example is as follows. A factory has two machines and one repair crew. Assume that probability of any one machine breaking down a given day is alpha. So, the alpha is the probability. Assume that if the repair crew is working on a machine, the probability that they will complete the repairs in 2 more day is beta. For simplicity, ignore the probability of a repair completion or a breakdown taking place except at the end of a day. That means, we observe the system at the end of the day, how many working machines in the system. Let x n be the number of machines in operation at the end of the nth day. Assume that the behavior of x n can be modeled as a Markov chain. So, based on the information available here, the machine can be breakdown and we have only one repair person, and the probability of he can do the repair in a day, that probability is beta, and 1 minus beta is the probability that he cannot be able to complete the repair of a machine in a day. And the random variable x n is it denotes how many machines are in the operation at the end of the day. Therefore, the possible values of x n, since we have 2 machines, the possible values of x n will be 0, 1 or 2. So, this will form a state space capital S. So, the S consists of the element 0, 1 and 2, and the x n over the n, it is going to form a discrete-time Markov chain, because it is a discrete time, a discrete state stochastic process, and also the based on the clue, the number of machines are working in any day depends on how many machines are working on the previous day and how many things are under repair and so on. So, the dynamics of the number of machines in operation depends only on the number of machines working in the previous day, not all the previous earlier days. Therefore, the memoryless property is satisfied by the stochastic process x n. Therefore, this is called a discrete time Markov chain. Our interest is to find what is the one step transition probability matrix with the assumption that the x n is the time homogeneous also. Since it is a time homogeneous DTMC, therefore, we are trying to find out what is the one step transition probability matrix for the given time homogeneous DTMC. So, this is the one step transition probability matrix P n, and the possible states are 0, 1 and 2, and suppose the system was in the state 0, 1 or 2 in the nth step, where the system will be in the n plus 1th step. Therefore, this is the possible values of x n plus 1 and this is the possible values of xn, and this one step transition probability matrix will give, suppose the system was in this state in the nth step, what is the probability that it will be in these states in the n plus 1th step. So, the first index will give what is the probability that 0, 0 in one step, that means in the nth step number of working machines are 0, and what is the probability that in the n plus 1th step also 0 machines are in the working condition. That means all are under repair, all 2 machines are under repair, and the probability of a crew is going to be not repair, that is going to be 1 minus beta. Therefore, the probability is 1 minus beta. In one step, what is the probability that the number of working machines going from 0 to 1, that is because of the crew is finishing the repair in a day, and that probability is beta. And since he can do the only one repair in a day, therefore, the possibility of repairing more than one machine in a day, it is not possible, it is a rare event, and the probability is going to be 0. Therefore, P02 is going to be 0. And similarly, now we can visualize what is the probability that number of working machines is 1 in the nth step, and what is the probability that in the 0 machines will be working in the n plus 1th step. That is possible with the 2 independent things. The one machine can be failed, and the other machine cannot be finishing the repair. Therefore, the crew is not finishing the repair, that probability is 1 minus beta multiplied by one machine is going to be repaired. Therefore, the total number of machines working will be 0 in the n plus 1th step, that is alpha times 1 minus beta. And similarly, you can evaluate the other element also. And for example, the system is going from the state 2 to 0, that is nothing but at nth step 2 machines are in the working condition, and in the n plus 1th step 0 machines are the working condition. That means both the machines got failed in the same day. Therefore, that probability is alpha times alpha, that is the probability both the machines got failed in the same day. Therefore, in the next day the number of working machine is going to be from 2 to 0. Like that, you can visualize the other elements also. The same one step transition probability matrix can be visualized with the state transition diagram, and the state transition diagram you have to make with this state space as the vertices or the nodes, and the weights of the directed arcs are nothing but the one step transition probability of system is moving from one state to other states. Those are going to be the weights. If the probabilities are zeros, then no need to draw the directed arc from that particular node to the destination node. So, first you start with the nodes as the possible values of the state space. So, you list out all the state space as a node. Now, by seeing the one step transition probability matrix, you should make the arc from 0 to 0. Self loop is allowed if the probability is going to be greater than 0. So, you should draw the self loop from 0 to 0 with the arc value 1 minus beta, and you should draw the arc from 0 to 1 with the arc weight beta, and you should not draw any arc from 0 to 2 because that probability is going to be 0. Therefore, 0 to 0, that probability is 1 minus beta, and 0 to 1 it is going to be beta, and there is no arc from 0 to 2 because that probability is 0. And similarly, now we can go for filling the second row. So, 1 to 0 is alpha times 1 minus beta, 1 to 1 is 1 minus alpha times 1 minus beta plus alpha beta, and 1 to 2. So, you have all three probabilities are greater than 0. Therefore, 1 to 0, that arc is alpha times 1 minus beta, and 1 to 1 is 1 minus alpha times 1 minus beta plus alpha beta. 1 to 2 is beta times 1 minus alpha. Similarly, you can draw the arc for 2 to 0, that is alpha square, and 2 to 1 and so on. Therefore, 2 to 0, that is alpha square, and 2 to 1 is 2 alpha times 2 alpha times 1 minus alpha, and 2 to 2, that is 1 minus alpha whole square. So, the state transition diagram is a pictorial view of a one step transition probability matrix. This is nothing to do with the initial probability distribution. It gives only information about whenever the DTMs is a time homogeneous. Suppose the system start from one particular state, what is the probability that the system will move into the another states with the probability, and it won't give more than that information, but this much information is useful when you are going to study the properties of the discrete time Markov chain, as well as when you want to find out the limiting distribution, that is the distribution of x n as n tends to infinity. The diagram will be very useful to conclude whether the limiting distribution exists or not, if it exists, whether it is going to be unique or not, and so on. So, those things can be visualized easily by seeing the state transition diagram. Now, I am moving into the second example. In this example, I have taken the barbershop example, which I have discussed in the model 1 also, the same example. So, the owner of a local one chair barber shop is thinking of expanding the shop capacity because there seems to be too many people are turned away. Observation indicate that in the time required to cut one person's hair, there may be 0, 1 and 2 arrivals with the probability 0.3, 0.4 and 0.3 respectively. So, this information is very important. That means during one person's haircut, what is the probability that no people turned up with the probability 0.3, and 1 people may turned up with the probability 0.4, and there is a possibility 2 arrivals is possible during the one person's haircut with the probability 0.3. Therefore, the summation of probability is going to be 1. So, during the one person's haircut, these are all the only 3 possibilities are possible with the 0 arrival or 1 arrival or 2 arrival. The shop has a fixed capacity of 6 people, including the one whose hair is being cut. That means maximum 6 people can be allowed in the system. So, 5 people can wait maximum and 1 people under the service. Any new arrival who finds 6 people in the barber shop is denied entry. That is the meaning of capacity of the system is finite with the size 6. Now, I am going to define the random variable. Let x n be the number of people in the shop at the completion of the nth person's haircut. This is very different random variable, or this is very different stochastic process. Usually, the parameter space is time, but here the parameter space is the number of people in the shop. The n is the parameter space is the person who leaves after the haircut. So, it's a nth person who leaves the system, that becomes the parameter space, whereas the random variable is how many people in the system when the nth person leave the system. That means, you should not count that person when you are finding the values of x n. That means, this number is counted at the departure time point. So, when the nth person leaves, how many people in the system, and the system is maximum 6 people allowed. Therefore, he cannot see more than 5 people in the system when he leaves. So, because of this constraint, because of during the one person's arrival, either 0 or 1 or 2 arrivals can take place and so on. Based on this information, the stochastic process x n is going to be a discrete time, discrete state stochastic process, as well as the Markov property satisfied. That means, the probability of x n plus 1 take some value, given that all the previous values are known, that is same as the conditional probability distribution of x n plus 1 takes some value, given that x n was some value. So, the future distribution, given that present as well as the past information, is same as the future distribution given the present, not the whole past information. So, this Markov properties will be satisfied by this stochastic process. Therefore, this x n will form a discrete time Markov chain. Obviously, it is the time homogeneous discrete time Markov chain also. So, in this example, our interest is to find out what is the one step transition probability matrix. This is going to be the one step transition probability matrix, and the possible states S is going to be 0, 1, 2, 3, 4 or 5, because the capacity of the system is 6, and whenever the nth person leaves, either first person, second person, third person leaves, how many people are in the system? Therefore, the maximum will be 5, and there is a possibility when he leaves, no one will in the system also. And this is the one step transition probability matrix, and this is also going to be a square matrix, because it is going to be a countably finite number of elements, and this is the 0, 1, 2, 3, 4, 5. Now, we can discuss what is the probability that 0, 0 in one step. That is nothing but in the nth, when the nth person leaves, no one in the system. When the n plus 1th person leaves, no one in the system. What is the probability for that? That is x n plus 1 is equal to 0, given that x n was 0. It is a one step transition probability. It is independent of n, because it is a time homogeneous. It is a one step transition probability matrix. So, this is possible at some person leaves, whatever be the n, nobody in the system. When the next person leaves, nobody in the system. So, that is possible by when some person leaves, the system was empty for some time, you do not know how much time it was empty. Then the n plus 1th person enter into the system, and during his haircut, no one turned up, or no arrival takes place during his or n plus 1th haircut is going on. Therefore, when he leaves, no one in the system. So, we are not bothering when he enter into the system and so on. Our interest is how many numbers of people in the system when the n plus 1th person leaves, and this probability is n plus 1th person leaves, 0 people in the system, and given that when the nth person leaves, also 0 person in the system. So, that is possible with the explanation I have given. No one enter into the system during the n plus 1th person's haircut, and the information is provided indicate that the time required to haircut one person haircut, there may be a 0, 1 or 2 arrivals with the probability 0.3. So, no arrival takes place during the one person's haircut is 0.3. Therefore, this probability is possible with the probability 0.3. Whereas, P01 of one step, the same way you can write probability that x n plus 1 is equal to 1 given that x n is equal to 0. That is possible when the nth person leaves no one in the system. When the n plus 1th person leaves one person in the system, that means during his haircut one person enter into the system. That is possible with the probability 0.4. Similarly, from 0 to 2 in one step, that is going to be 0.3 with the probability 2 arrival takes place during the n plus 1th person's haircut. Now, the second row. Second row, what is the probability that when nth person leaves one person in the system, when n plus 1th person leaves 0 person in the system. That is possible during the n plus 1th person haircut, there is no one in the system, no arrival takes place, therefore, that probability is 0.3. And from 1 to 1, that is possible with one person arrived during the n plus 1th person haircut, therefore, that probability is 0.4. And going from the state 1 to 2, that is possible 2 persons arrived during the n plus 1th person haircut. Whereas, from 2 to 0, that is not possible, because when nth person leaves the 2 person in the system, therefore, n plus 1th person in the leaves, definitely he will see one person in the system, because of no arrival and 1 arrival and 2 arrival. Therefore, it will be shifted by one column and it will be keep continuing till the end. Whereas, the last one, what is the probability that the 5 people in the system when the nth person leave and 4 people in the system when the n plus 1th person leave, that is same as no arrival takes place during the n plus 1th arrival, n plus 1th haircut going on. So, therefore, this is going to be 0.3. Whereas, P 5 to 5 in one step, that is possible with the combination of one person arrive the system or 2 person arrive the system. This system size is going to be maximum 6. Therefore, when n plus 1th person haircut is going on, if one person arrives, then he will be entered. If 2 person arrives, then he cannot be accommodated. Therefore, he won't join the system. Therefore, the system, the number of customers in the system in the x n, that is going to take the value 5, and the combination of 0.4 as well as 0.5. Therefore, this probability of system is moving from 5 to 5 is 0.7 because of 0.4 plus 0.3. Now, I can give the state transition diagram for this example, because S is going to be 0, 1, 2, 3, 4, 5. Therefore, the nodes are going to be 0, 1, 2, 3, 4 and 5, and the possible values from the from the one step transition probability matrix I can make out. So, 0 to 0, that probability is 0.3 and 0 to 1 is 0.4 and 0 to 2 is 0.3. Similarly, I can fill up the all other things, and 5 to 5, that is very important, and 5 to 4, that is possible with the probability 0.3, and 5 to 5 is possible with the probability 0.7. So, this is the state transition diagram. I did not complete the state transition diagram. We have to fill up all the arcs with the weights going from one arc to other arc with the positive probability. Wherever there is a probability 0, we should not draw the arc for it. So, in this lecture we have discussed the discrete time Markov chain, then we have given the few important properties, followed by we have explained the one step transition probability matrix, and also we have given two simple examples. With this the lecture 1 is over for the module 4. Thanks.